Hello, everyone, and welcome to the Computational Social Science Seminar. Today, we have a special guest, Professor Ingo Scholtes, who is Professor for Machine Learning for Complex Networks at the Center for Artificial Intelligence and Data Science of Julius-Maximilians University of Würzburg. So that's a very long title. He is further SNSF professor in the Department of Informatics at the University of Zurich, where he heads the Data Analytics Group. His research addresses open questions at the intersection between machine learning, network science, graph mining, and computational social science. A summary of his foundational works on higher order graph analytics for time series data was recently published in Nature Physics. So congratulations to this great achievement.
Thank you.
In 2014, he was awarded further on a junior fellowship from the German Informatics Society. In 2018, he received an SNSF professorship with a volume of 1.5 million Swiss francs from the Swiss National Science Foundation. And since 2021, he holds the chair of Computer Science 15 in Würzburg. He's founding co-chair of the Computational Social Science section of the German Informatics Society and associate editor of EPJ Data Science. I'd also like to welcome Frank Schweitzer, who has actually established that journal and is with us today. But back to Ingo, he will talk today about new developments in the modeling of higher order dependencies in network systems. Welcome, Ingo, and the screen is all yours.
Yeah, thank you very much, Dirk, for this very kind introduction. So I guess one of the signs of getting old is that the credentials get longer. It's a real pleasure here to speak to you. It's always great to speak also to students with interdisciplinary backgrounds. And I think it's also a great opportunity because this is one of the few talks where you really have an hour to talk about things. And I will use this as an opportunity to give a little bit more of an unusual talk. I think I have talked twice here in the Computational Social Science Symposium in the past years in the seminar. And I have always talked about our works on computational social science. And today I would like to take the opportunity to talk about something completely different, which is more our methodological works and machine learning works. And even this talk I would like to give in a little bit unusual way because I want to take a more, let's say, historical and philosophical perspective that is more related to some fundamental questions of how we should model complex systems. Okay, I will also have a little interactive demonstration in which I exemplify some of these higher order models that we will talk about and how we can apply them to a fairly simple data set, we would think, but hopefully the message will get across that also these simple data sets are sometimes actually really complicated to model once you start thinking about it in a bit more detail. You should also have access to the material. So I have provided a link that includes not only the slides for your reference, but also 2 Jupyter notebooks, or at least 1 Jupyter notebook with a little toy example that you can actually play with yourself. But I will demonstrate this and I will mention it again in the middle of the talk. Okay, so I think, first of all, before I talk about the topic, let me just spend a few words on myself and what we are doing research-wise. So as Dirk kindly introduced, I'm heading the chair of Informatics 15, Machine Learning for Complex Networks in Würzburg. And in a nutshell, we're basically interested in 3 different lines of research that you could summarize by, basically machine learning, network science, and computational social science. In the first line of research, we are generally interested in machine learning techniques for all kinds of complex relational data. Complex here can mean complex relational structure, complex temporal structure, or it could also mean noise or errors that we have to account for in the data. A second line of research that I will talk a little bit about today is our work on extending network analysis and graph mining and graph learning techniques for time series data. And then we also have a third applied line of research in which I have actually collaborated for many years with Frank and his collaborators where we actually apply those techniques to better understand social systems in terms of computational social science applications. Yeah, and I think also in these grim times, it's always good to start with something positive. So I can also tell a little bit about my hobby. So I'm not only doing research, but I'm also enjoying landscape photography. So for instance, going to the mountains, which I guess Zurich and the area gives plenty of opportunities, or going to the north, or also engaging in astrophotography. Here's actually 2 examples for some recent pictures that I took. And I'm showing you this for a specific reason, because this is not only a beautiful image maybe, but it's actually also a great opportunity to introduce the more general theme of the talk today, which is machine learning and data science. And before we can introduce what learning and science actually is, or before we can introduce what machine learning and data science is, we first have to understand what learning and science is. So we can understand this by having a look at the usual scientific method, which basically consists of 3 steps. And the first one is that we observe our environment. So we observe a system. And this image of the galaxy, the Andromeda galaxy that I have shown, is not only just an image, but you can also say it's a scientific observation. And from such scientific observations, for instance, the redshift in the light of galaxies or the motion of planets, stars, and galaxies in the night sky, we can actually infer models that try to explain the phenomena that we observe. And in this case, for instance, the model that explains the motion of celestial bodies would, for instance, be the model of general relativity. Well, a good model not only explains what we are observing in the data, but a really good scientific model also makes predictions that we can actually verify in further observations. And that's exactly what happened here in this case, because from these observations of galaxies, for instance, this general relativity model was inferred. And one of the predictions of this model is that in the center of such galaxies like the Andromeda galaxy, there should be actually a black hole. And just 2 years ago, such a black hole was directly observed for the first time, which gives basically further credit to this theory, to this model of general relativity. So this cycle that consists of observation, modeling, and prediction is called the scientific method. And computers have revolutionized it over the past decades, you could say. First of all, we need human intuition to infer a model from observations, like for instance, in the case of general relativity. But the other steps in the process have been revolutionized by computers, like for instance, formalizing mathematical models in terms of algorithms and computational methods in order to derive predictive models, and then using those predictions and basically validating them in huge amounts of observational data using, for instance, advanced data analytics techniques. And in fact, this previous example with the direct observation of the black hole is a perfect example for this, because an incredible amount of data collection and also data, very advanced and sophisticated data processing went into the creation of this image that I have just shown you. So you see that one thing where we still need human intuition in this traditional scientific method is in how we model phenomena in our environment. And this is exactly where machine learning gets interesting, because machine learning refers to algorithms and methods that can also automatize this aspect of the scientific method. So, and this explains basically what data science is, because data science now collectively refers, according at least to my definition, to the methods, the processes, and the algorithms that we use to extract knowledge from large volumes of unstructured and noisy data. And you see, machine learning is one important component in data science, but certainly not the only one, because we can think about agent-based or predictive modeling techniques, or data science and data analytics, or statistical data analysis as well. So what this definition of data science leaves basically wide open is what kind of models we are actually using to understand complex phenomena in our surrounding. Like, for instance, here, just equation, a mathematical equation that we can use to model something. Well, in the past decades, by studying many different complex systems, an interesting modeling framework has become very popular, which uses graphs or networks. So you can think about complex systems like information systems, like the whole of the Wikipedia system, for instance, or social systems, or large scale or even global scale technical infrastructures like communication networks or transportation systems. A common aspect of those systems is that we can model them as a system that consists of a large number of interacting elements, and we often use graph or network models to capture these elements and the interactions between them. Like, for instance, here we can represent certain transformer stations and power plants as nodes. Here we can represent agents in a social network as nodes and the interactions between them as edges, or we can represent Wikipedia articles as nodes and the hyperlinks between them in terms of edges. The great benefit of this approach is that it gives us a almost universal mathematical language to describe a wide variety of complex systems that consist of those many interacting elements. And one example that we can look at a bit closer is we can think about data on social interactions. In this case here, these are data from, this is, I think, GitHub data on an open source software community, where we have the nodes being the developers and then the directed interactions between them being communication via email. So what we can do now with these representations is, for instance, we can apply modern graph learning or machine learning techniques to infer latent features of nodes. So we can try to explain the topology by which the nodes are connected based on some latent features that we may not directly observe in the data. And there's machine learning techniques that do just this. And one specific type can be used to find also groups of similar entities, so cluster structures, for instance. So here we see, for instance, that we could more or less naturally cluster this social network into two different groups that are only loosely connected. And we can use those techniques, for instance, to develop recommender systems, because they define groups that are more similar than groups of nodes that are more similar to each other than in other groups. What we can also do in social network analysis is we can apply, for instance, centrality measures to identify influential individuals, or we can, in general, apply network-based models and dynamical process models to such systems to understand collective phenomena in complex systems. And that is something that is very actively done in network science and complexity science. Now, network science and generally graph learning techniques have become tremendously popular over the last years. So there was just an interesting perspective on this in Communications of the ACM that was published in September 2021 that is arguing that the future of data science and machine learning is really the ability to learn in big graph data, because graphs are such a universal and powerful abstraction. And I would like to take this opportunity to explain a little bit, not only explain a little bit the popularity of network science, but also give a little bit of a historical overview of what I would call different ages of computer science. And I would like to model this in analogy to these different ages in Tolkien's mythology. So for those of you that are aware with this mythology, there's different ages that are separated from each other by some cataclysmic event. So something in which the world is basically changed, and then a new age with new developments, a new geography, new peoples basically starts. So in Tolkien's mythology, there's three ages. There's the first age, the second age, and the third age. And in network science, I would argue that we can actually identify similarly three different ages, where the first one refers to the theoretical foundations, which we can actually trace back until the 1730s. The second age I would call the age of interdisciplinary applications of network science, which we can trace back roughly to the 1870s. And the third one, which is now very, very popular, is the development of machine learning techniques for network data, which in its first roots, we can even trace back until the 1960s. And what I would like to do now is I would first like to introduce this historical perspective And then from this historical perspective, I would like to motivate some new developments, which I think have the potential to generate interesting challenges for all of these different areas in which network science is being addressed. So let's start with the first age, the creation of the theoretical foundations. So many of you will be aware that network science has its origins actually in the graph theory, so that's a mathematical discipline which can be traced back to, well, in fact, a Swiss mathematician, Leonhard Euler, who published the first work that you could say is a graph theoretical work in 1736, which is the famous study of the Königsberg bridges problem. So in a nutshell, the question was whether there is a way that you can actually walk between all parts of the city of Königsberg by crossing each of the 7 bridges exactly once. This is a mathematical problem. And the great achievement of Euler, and that is something that informs our general view on graph and network models and what they can actually do, is that he realized that this is actually not a geometric problem. It is absolutely irrelevant where exactly the bridges are and where in space the different areas of the city are located. What he realized that this is not a geometric, but a topological problem. So the only thing that counts is what entities exist, the different parts of the city, and how are they interconnected by the bridges, which he represented in terms of the links. So what he really made was a fundamental abstraction that reduces this problem to its absolute minimum, and that allowed him then to reason about a solution of the problem. And so this was the first use of what you could call a graph model of a real-world phenomenon. And the usefulness of this graph representations and graph theoretical findings was soon after discovered, like for instance, in representation of maps, graph coloring problem. So if, for instance, you want to color different regions, different counties in a map with colors so that always 2 adjacent regions have different colors, this is basically a topological problem, and that was already discovered in the 1850s in the first formulation of graph coloring problems. Or in the 1850s, also people started to talk about things like that we call today tree graphs, so graphs that have very specific structures. So an interesting aspect of this work on the Königsberg bridges is that it was not only, you could say, the big bang of graph theory, but it was also one of the big bangs of a mathematical field that is called topology. So this is the field where really the question of what is connected to what is in the center of its study. And graphs and topology were always closely linked. So already since the 1750s, there were first works that actually linked these two, and that could be seen as the first works in the mathematical discipline of topology, like for instance, Euler's work on the polyhedron theorem, which basically relates the number of vertices and edges in a graph representation of a convex polyhedron. Or the use of Cayley graphs in the 1870s to represent mathematical structures that we call groups, or works on conditions for graph planarity, like the Kuratowski theorem in the 1930s. An interesting development in the 1950s, which was basically instrumental for what we today define as network science, was the combination of 2, at first glance, very different areas in mathematics, statistics and probability theory and graph theory, into what we call now random graph theory. So the idea is to formulate simple stochastic models that generate different types of graph topologies, and then being able to study those probability spaces of graphs in terms of what are expected properties of graphs given certain conditions. So that means we are able to formulate distributions on graphs, and we can argue in a statistical sense about graphs. And based on this, also first works about spectra of finite graphs, or different types of statistical models for graphs, for instance, with prescribed degree sequences, proved to be instrumental for complex networks studies and network science. And then really since the 1990s, we are talking about what we now call complex networks, where on top of simple random graph structures, we are now starting to model more of the complex real-world characteristics of networks that appear in reality, like for instance, transportation networks or social networks. And where we also get a better understanding how collective dynamics is influenced by the topology of those systems. For instance, synchronization dynamics, or how scale-free structures influence robustness of systems, or how the degree distribution influences epidemic spreading. So something that we have all experienced now in reality, unfortunately, over the past 2 years. So this is the first age of the theoretical foundations. And now you could ask, okay, so what's then triggered the move towards a second age of graph theory or network science, which I called the interdisciplinary network science field? Well, I would say this is the rise of empiricism. So that means the idea that we are using data and observations to reason about the world. And I think from today's perspective, it's actually quite valuable to highlight again that our current understanding of science was not always the understanding of science, right? So before the 18th century, there was this dominant paradigm of what is now called rationalism, which sees science as an objective search for infallible truth. An objective means here that a scientific discovery, a scientific insight should in no way depend on the person basically making it. And that also means that it should be independent of the specific experience of this person. And that is something that was changing rapidly in the 18th century by scholars like, for instance, David Hume, who said that, well, fundamentally, all human knowledge is based on experience, empira. So that means we have to get evidence, for instance, by making experiments, by observing, and only in this way we can actually create knowledge. So this was really a fundamental paradigm shift in science. And soon after, this also led to new areas in other scientific disciplines. For instance, suddenly also this whole question of what is the quality of data, what kind of errors or dependencies exist in empirical observations became very important. Like, for instance, works like the works by Gauss on the normal distribution, or first works on, you could say, statistical learning in terms of least square regression date back to the early 19th century. Or reasoning about uncertainty in orbital predictions, which kind of acknowledges the idea that we can actually never accurately measure a phenomenon. We have to explicitly model how wrong our measurements are to get an understanding how wrong our predictions are based on the models, which is something that occurred again in the early 19th century, or fundamental works on statistical inference like significance tests actually that date back to the late 19th, early 20th century. And in the 20th century, there was again a paradigm shift, which we now call the critical rationalism, with proponents like Karl Popper, which again basically criticize one of the foundations of the rationalist view of science, but not so much the objective part, but the part that we are looking for infallible truth. So that means a fundamental difference in critical rationalism compared to rationalism is that it kind of assumes that a theory must be able to be wrong in order to be a scientific theory. So that means now the focus was not on infallible truth anymore, but on falsifiable theories that actually make testable predictions. So that is our current understanding of what a scientific theory is and how we actually collect knowledge in this cycle of observing, modeling, predicting, and then trying to validate our predictions, or invalidating our models actually. Okay, so this rise of empiricism also now had an impact on how network models are used, because you see that in the first age of network science, with all of the works that I had on this previous slide, they all had one thing in common. There was no data in there. So that means this was all based on more or less theoretical models, like random graph models or synchronization models in networks that have a degree distribution that follows a certain distribution. This is not necessarily based on data, but it's a more fundamental insight into how the topology of systems influences, for instance, dynamical processes. Starting in the 1870s, people actually started to use graphs to model actual observations. So using graphs in an empirical sense, you could say. Not surprisingly, maybe, they were actually first used even under the term graph in the 1870s in chemistry to represent chemical molecules. Maybe this is not so surprising if you think about the fact that, well, chemistry is fundamentally involved with understanding the connections between atoms. So a graph seems like a very natural representation for that. And by the way, Sylvester was not only the person that for the first time actually used the term graph, but he also used for the first time the word matrix, which is now widely used in mathematics. In the 1920s, people started to use graph and network models to model food webs in ecology. Then in the 1950s to model neural networks, in the 1960s to model gene regulatory networks. So that means now we are seeing more and more interdisciplinary applications of network models to understand complex systems that consist of interacting elements, which was not really the focus initially of graph theory. In the 1930s, there was an interesting development that for the first time, at least that's the first reference in the social science literature that I could find, Moreno used graphs to model social systems. Back at the time, this was called the so-called Sociogram. And here is what I believe is the first depiction of a social network in social science literature. Maybe I'm wrong, but that's the first one that I found, where here actually the nodes represent actors in a cottage family and the links represent different types of interactions between them. And then based on this graph representation, people started to think about how can we measure certain aspects of the topology and how they relate, for instance, to nodes by introducing things like closeness centrality, or by developing methods to quantify the amount of clustering that exists in a network, or trying to categorize different types of social interactions in terms of streak or weak or strong ties, like, for instance, this famous work by Granovetter in the 1970s. And then what we see, maybe starting in the 60s, but I think really taking off in the 80s, 90s, and 2000s, is the use of complex network models and network science techniques to model critical infrastructures. Simply because the world became more and more connected. So with increasing mobility, with increasing large scale and even global scale infrastructures, networks were used to model transportation networks, like, for instance, first time in the 1960s. They were used to model the robustness of internet topologies in the 1990s, or now increasingly also to model economic systems and resilience of socioeconomic systems. So a very exciting area of research that has led to many fundamental insights about, for instance, robustness and resilience of complex systems based on network models, and sometimes also in a combination between network models and agent-based models. So again, this is the second age. So what development then would trigger what I would think is a third age of network science? Well, I would argue this is the rise of big data and machine intelligence. In order to understand what has fundamentally changed in the past, maybe 2 decades or so, it is actually quite interesting to remind ourselves that there's estimates that up to the year 2003, that humanity as a whole has produced approximately 1 exabyte of data. So 1 exabyte is not what you usually have on a hard drive or a solid state disk, unfortunately. It's about 1 billion gigabytes, and it's an amount of about 1 trillion images of the average size that you can find on the internet. So this means this 1 exabyte includes everything that humanity ever produced, like all of the text, all of the images, everything in terms of data, including things like the Winchester manuscript from the 1900s. Now, in 1994, the World Wide Web was becoming popular with what is now the web giants being founded in short succession. And something changed fundamentally. And now in 2021, thanks to the World Wide Web and online services, data and smart devices are basically everywhere. So now we have more than 3 billion smartphones that are being used alone. And there's estimates that now the amount of data that was produced by humanity up to 2003 is now produced every 48 hours. So you see, there's a fundamental shift across human history in terms of what has happened just over the past 2 or 3 decades. And this increasing importance of data has led, and also the increasing availability of computational resources has led to what could be called an AI hype, so a hype in machine or artificial intelligence. I would say even reloaded, because we have seen this already. In the 1960s, many people don't know this, there was a first huge AI hype with a lot of inflated expectations of what artificial intelligence actually could do within the next 2-3 decades. And actually a good example for this is the movie 2001, which is fundamentally about the relation between artificial and human intelligence, you could say. It's also a science fiction movie, and this was, I believe, released in 1967. So this was in this first AI hype. But then triggered by some more critical reports on what at least contemporary AI in the 1970s could actually do, in the 1980s, we experienced what is now called the AI winter. So that means it was a phase of, you could say, disappointed expectations. And then only in the 2000s, with the advent of deep learning, and I would argue even more importantly, with the advent of GPUs, which leads deep learning to be also cheap learning, we see another area of maybe not inflated expectations about what artificial intelligence can do, both in industry, media, and also in science. So, and this has also influenced, obviously, how we are thinking about networks. So the question of how we can actually learn in data that can be represented as graphs or networks is, again, as old as the first techniques in artificial intelligence. Like, for instance, first techniques in finding clusters, not in general data, but in graph data, date back to the 1960s and the 1970s. And it's still a very important and popular topic in graph learning and network science. In the 1990s, with the advent of the World Wide Web, we also see fundamentally new applications of network science and graph learning techniques in terms of recommender systems. So now we are using graphs to represent relations between people, relations between information items, and we're using their topological structure, for instance, to rank information in terms of page rank, to factorize or to infer latent features based on matrix factorization techniques, or to find similar pairs of items that we can use in recommender systems using techniques like SimRank, or, for instance, predicting missing links in networks, which is now a technique that is used to recommend friends on social media like Facebook or Twitter. And in the 2010s, again, a fairly recent development now, there's a new interesting area of works that combine deep neural networks with graph data into what is sometimes called graph neural networks, or more precisely, for instance, graph convolutional networks, which generalize deep learning techniques that are commonly only applied to some points in a vector space, or to some two-dimensional grid structures, like, for instance, applications of deep learning to image data, now to graph data, which can have arbitrary topologies. So this is extremely popular, and they are widely applicable and very highly cited works, for instance, DeepWalk, Line, GCN, GraphSage, that, for instance, can be used to generate vector space representations based on graph data. Like, for instance, here, this example of a citation network, which is then transformed into a feature space so that we can also apply downstream machine learning and deep learning techniques to it. So this, I think, led to a fundamentally different type of works on network science, which are not exactly, again, involved with understanding collective dynamics in complex systems, but more like understanding how we can detect pattern in data that is actually structured as a graph. So all of these techniques are very powerful because we can apply them to all kinds of data on real complex systems. And as I said before, the large benefits that we have with graph models and network science is that it's actually such a universal abstraction. And it's universal because we can apply it to a system whenever we have relational data that tells us which element in the system is connected to which other element. So that means whenever we have some dyads, some pairs, we can basically turn this into graph representation, and then we can apply all of the techniques and the results that have been developed over a area of more than 300 years. And that's certainly a very appealing fact, but unfortunately, maybe this is not enough. Because now that we have more and more data, but even more importantly, also more richer and also more high resolution data, we find that relational data on real systems is often more than just these dyads that we represent in a graph model. Like, for instance, relational data is often multidimensional. So that means, for instance, we have multiple types of interactions. So that means we have some additional attributes on interactions that would be just discarded if we represent all of them as a simple graph with a single type of interaction. Or real data is time resolved. So that means we additionally have timestamps and a temporal ordering of the interactions that we again discard if we apply standard graph and network science techniques. Or data is multirelational. So that means it's not fundamentally about dyads, but it's about larger groups of nodes interacting. And that's again a piece of information that we discard if we just study graph models. So these are examples for higher order interactions or higher order features in real data on complex systems that are often not really well represented when we are applying network science techniques. And I would make the statement here, and there's other people that say this as well, that we really have to rethink on how to apply network models, because chances are that we cannot fully understand complex systems by projecting the rich data that we now have available to these simplistic graph models where we just have nodes and links. And this is something, an insight that many people have gotten over the past maybe 3, 4, 5 years. And it's an extremely popular field in network science and data science in general, I would say. And maybe it's so popular because once you start to think about it, and once you have seen what else is in the data that you want to study, and once you have learned about techniques that you can use to do that, it's very hard to go back. Because once you have seen the full complexity of the system, you fundamentally see a standard graph model as an oversimplification, and you become more skeptical. And we have summarized some of the research on this field in this perspective article that we published in Nature Physics, which Dirk mentioned in the beginning of the talk. Now, what I would like to do now is I want to not only talk about our own works in this area, I want to give a little bit of an overview of what different modeling paradigms exist that model different aspects of higher order interactions that we can find in different complex systems and that we think are very important to consider. And this involves different challenges, and it also involves different mathematical frameworks and different solutions to address these challenges. The first challenge, you could say, is actually as old as social network analysis, because in many systems, we actually observe that elements can influence each other, not only via a single type of interaction, but with more than one type of interaction. And even if we look at the oldest depiction of a social network, we see that Jacob Moreno actually depicted the social network in 2 colors. So he had red and black links, and he used that to model friend and foe relationships that he got from a survey of the Scottish family. So that means there's 2 fundamentally different types of relationships, a positive and a negative relationship. This translates to, for instance, works in epidemic spreading that use contagion models with multiple transition modes, because you can imagine that, for instance, an epidemic will probably spread differently across friend links than foe links, because maybe foes rather avoid each other than making frequent contact. This has been incorporated into epidemic spreading models. Or we can think about also large-scale infrastructure systems where we often have multimodal transportation systems, for instance. So that means we not only have a single type of transportation in the system, but we can switch between different types. For instance, in an airline network, we might be able to switch between different airlines, which might be costly because you have to switch terminal, or you are outside of a certain alliance between airlines, which makes refunding tricky if you miss your flight, right? So there is a difference whether this is a Lufthansa flight or this is a Air France flight. Or think about multimodal transportation systems in a city, where switching between trams might be easier than switching between a tram and a S-train or a bus, for instance. So these are information about systems that we want to somehow incorporate in our mathematical models. And this is something that is addressed by a specific type of higher order network models, which we could say address different forms of typed interactions. So this idea that interactions can be positive or negative, they can be basically plus or minus, is actually very old and has been addressed already in the 1950s with the introduction of what is called sign graphs. So it means we have networks where we not only have links, but we can have positive, negative links that are represented by negative and positive entries in an adjacency matrix. And then we can actually generalize also some mathematical formalisms on adjacency matrices. For instance, what does a path mean if the sign is positive or negative if you multiply adjacency matrices to this representation? Or in the 2010s, so roughly 10 years ago, the research on multiplex and multi-layer networks became extremely popular because, again, people started to understand that standard network science techniques are just too simplistic to understand these real systems. So in order to model networks with multiple links, people proposed to study so-called multiplex network models. So multiplex, because we are talking about multiple layers of connectivity that interconnect basically the same set of nodes. So the assumption of those models that use multiplex models is that we have identical nodes across the layers. And you see that links can only be connected within, nodes can only be connected within one layer. So it means we cannot have connections that are outside the layers. And the dashed lines here just indicate that those are the same nodes that are represented in multiple layers of connectivity in the system. And different from that, there's a different mathematical formalism of so-called multi-layer or multi-layer networks, or also networks of networks, where we basically relax that constraint that the nodes have to be identical in all of the layers and that they cannot be linked across the layers. So here we could have different layers that contain different nodes, and we can have links that are within one layer, and we can have links that go across layers, and they can have different meanings as well. And mathematically, we can represent this in a graph theoretic way using multigraphs with edge labels. And now we can think about how we can generalize findings from network science, from social network analysis to this type of more complicated graphs. So this is one important line of research that has proposed different higher order modeling techniques that account for different types of interactions that are usually, so information that is usually discarded when we study standard graph models. A second important type of higher order patterns in real systems is that often interactions actually naturally involve more than just two elements. So think about group interactions in social systems or in ecological systems. In fact, the term of higher order interaction is something that is actually quite old in ecology. So in this 1990s ecology paper, this paper already states that we cannot understand complex ecological systems based on observations of interactions only between pairs of species, because we have to account that sometimes an interaction is only possible if more than two species are together in an ecosystem. So just breaking this up into pairs kind of misses the complexity of that system. And there's different types of data that have this property. So group interactions in ecological or social systems are one example, but also all kinds of co-occurrence data, like for instance, who is at the same place at the same time. This can be more than pairs, and we want to kind of recover the information that it's a group of 7 people that has been together at the same place at the same time. Or think about co-authorship relations. So that means people co-authoring papers. These papers can be co-authored by more than just 2 people. And probably if it wouldn't have been for the specific group of authors that actually worked together on this paper might not have emerged in the first place. So that means, again, this is an information that we want to recover. So here's an example for that. And I will give you a more practical example in Python in a moment, an interactive one. So here's a set of co-authorship on 1, 2, 3, 4, 5, 6, 7 papers, where we have pairs of authors, we have groups of authors of 4 and 3, and this would be a standard network representation where we represent those co-authorships with 13 dyadic links. And you see that we lose the information on which papers were co-authored by whom by making this dyadic projection. Now, how can we get around this problem? By using higher order models. Well, there's different types or families or paradigms of higher order models for polyadic interactions that have been proposed not only in the past years, but in the last decades. But there's a renewed interest in this since, I would say, 4 or 5 years, because we just understand that actually many data that we have studied as networks are fundamentally non-dyadic. So one approach uses a mathematical abstraction that is called a simplicial complex. And this is, again, this is a result from the mathematical area of topology that dates back to the 1930s. So what is the basic idea? The basic idea is that we can generalize a link to something that we call a K-simplex. And a K-simplex interconnects a set of K nodes in a network. So that means if you consider an undirected edge, which connects a pair of nodes, that would be an example of a 1-simplex. So a 1-simplex connecting 2 elements, a 2-simplex connecting 3 elements. So that means this co-authorships we could model as a simplicial complex where we have 4 1-simplices, which capture 4 dyadic interactions. Sorry, this should be 5, right? Because we have 1, 2, 3, 4, 5 here. So we have 1, 2, 3, 4. So I think this is not matching actually the co-authorships that I indicated here. Sorry for that. So those links would be between pairs of nodes. And then you see we also have a co-authorship with a group of 4 authors and a co-authorship with a group of 3 authors that would be represented by a 2-simplex and a 3-simplex. And we often visualize this in terms of, yeah, basically geometric primitives, like here this triangle or this polyhedron in the visualization. So that means this triangle, this filled triangle here would indicate a 3-fold interaction between E, F, and G. And this polyhedron would cover the group of A, B, C, D of 4 nodes. So that would be a 3-simplex. And now there's an important assumption that is very important to understand in simplicial complexes. And this is that there is downwards closure. So that means every K-simplex automatically implies that the lower order simplices also exists. So that means in a geometric way, we can say that every face of such a K-simplex is again a simplex of lower order. What does this mean? Well, there's no lower order from a 1-simplex, but a 2-simplex actually contains 3 1-simplices, which are the 3 edges here. And those 3 edges would be automatically included in the 2-simplex. A 3-simplex here, consisting of an interaction between 4 elements, would automatically include 1, 2, 3, 4 faces that represent 2 simplices, which are the different groups of 3 people within the group of 4 people that have collaborated, as well as all of the 1-simplices that indicate pairwise interactions. So that means with this model of a simplicial complex, we fundamentally assume that we can form subsets and that those subsets are valid interactions as well. That makes it, for instance, useful for co-authorship networks, because we can say, well, if a group of 3 people have collaborated, then we can also say that all of the groups of 2 people within those co-authorships have interacted as well. But this is also how this approach is fundamentally different from a different higher order modeling framework, which is called Hypergraphs, which dates back to the 1970s. This is a different generalization of standard graph models with connections between dyads. You could say it's even a generalization of a simplicial complex, because we can actually represent a simplicial complex also as a more complicated hypergraphs, but not the other way around. Because the idea is that we can now form hyperedges which connect k plus 1 element for any k that we can choose, but without implying this downward closure. So that means we cannot form the subsets and assume that those are hyperedges as well. You see this in the example here. That would be an undirected hypergraph representation of, again, a co-authorship set, for instance. And here you see that we have a co-authorship between the three elements V3, V5, V6, but that does not imply that an edge between V5 and V6 exists or an edge between V3 and V6. So that means if we would like to tell that those lower order edges are included as well, then we would have to do it like here in the three-body interaction E1. So we have additionally a two-body interaction, which is represented by this additional set. So this is a fundamental difference in the assumptions. And this also means that we need to use different mathematical representations, and we need to use different generalizations of graph theoretic methods to those different paradigms. Now you could say, well, this is fairly simplistic because it kind of generalizes edges exclusively towards sets of nodes. And those sets don't really have a structure inside. And that's why actually more recently, there have also been different higher order models which kind of generalize those interactions to fundamentally non-dyadic, but more complicated, you could say building blocks of interactions as well, like for instance, network motifs. So for instance, instead of just using sets of three nodes, we could look at all possible three-node directed motifs in a network. And we could say, well, these are really the building blocks that our network is built from. And we can actually create generative models from these more complicated higher order interactions, or we can do things like generalizing adjacency matrices to such motif adjacency matrices, where basically two nodes are represented in the adjacency matrix if, as with a one, for instance, if they are present in the same three-node directed motif. And then, for instance, we can generalize clustering techniques in a way that they account for this fundamental higher order structure in the data that we might have. So also very interesting way to generalize network models to higher order interactions. Okay, so these are two frameworks that I just wanted to briefly mention, but there's also more complicated ways in how we can include or should include also higher order interactions in real data on complex systems. And let me give you a little example for this. And this now relates to time-resolved interactions. So it means systems that are fundamentally dynamic in their topology and where we have time series data that tells us not only when, not only who is connected to whom, but also when and in which precise order those interactions occur. Now, in the temporal networks literature, there have been various ways to address this, but I would like to make the point here that this is also fundamentally a higher order interaction problem. And let me explain what we see here. So in the left side, you see a set of four nodes, A, B, C, D, and you see a sequence of directed time-stamped interactions that are instantaneous. And I have basically unfolded this, this temporal dimension into a spatial dimension here. So that means here on the y-axis, vertically, I have the different timestamps from 1 to 30. So each slice tells you that, for instance, here an interaction between A and B happened at time 1 in the system. So it means that gives us the precise sequence of the interactions. So what are we often doing if we study such data? In some way or the other, we aggregate this in order to be able to represent it as a network. So either we could throw away all of the time information and just say, for instance, we count all of the interactions that happen between the pairs of nodes, and we represent this, for instance, as a weighted edge. Or we do this in certain time slices, and we get really multiple layers of connectivity at different times. That gives us an idea of evolving networks. But in fact, the point is the following, and this leads us back to the very beginning of my talk, when I mentioned that we have this unified mathematical abstraction where actually the edges capture the interactions between the nodes. And that's what we are doing here, right? So we only represent information on the interactions between nodes. And here we have discarded information on the temporal ordering. But my point here is that we are actually not studying networks because we are interested only in the direct interactions between the nodes. But more often, we are actually just using those direct interactions because we want to reason about indirect interactions. So all kinds of network analytic methods, random walk models, epidemic spreading fundamentally make this assumption that if A is connected to B and B is connected to C, then there's a path by which A can indirectly influence C via node B. You could say this is the whole point of a graph or a network model, to be able to make this statement on indirect influence based on the topology of direct interactions. So now, how does this path here translate in our little toy example? So we can have a look at the precise temporal sequence, and you see that indeed this path in the temporal sequence can be realized because the interaction from A to B occurs before the interaction from B to C. So that means A can first influence B, and then this influence can spread on to C in the next step. Think about, COVID-19. So if A infects B, then B can infect C in the future, depending on obviously the incubation time, right? But the temporal ordering would be valid for that. And now this is important to understand, because just by changing the temporal ordering of the interactions and without changing the actual topology of the system in terms of who's interacting with whom and how often, you see that this path in the system can be broken, because if the interactions here occur in the opposite way, there's no way how a virus can spread from A via B to C without having to spread backwards in time. So this is a fundamental aspect of dynamic networks, which is often neglected. The directionality of the error of time means that the temporal ordering of the interactions influences which nodes in a network can influence each other via path of causally ordered interactions. We also call those causal path. And there's a multitude of data that contain this information about causally ordered interactions. Think about time-stamped social interactions. So you have measurements of interactions at specific times. That gives you a sequence of interactions where you can actually trace causal path in time. Or think about statistics of any flow process, of any walk process, of any path, or also certain types of categorical sequence data, where actually the categorical sequence traces something that's actually spreading in a network. What we observe from this little toy example is that if we represent such temporal sequences using a standard graph model, where we just are interested in the topology or the frequency of dyadic interactions, we actually discard information on the timing and ordering of the interactions that determine the causal path. And we can say those causal paths determine what we can call the causal topology of a system. So that means not only who can influence whom in the system directly, but who can influence whom indirectly over time based on the temporal ordering of the interactions. And in fact, we can even measure the information loss that we experience if we aggregate networks based on some entropy measures that we have defined in this paper here. Okay, so this idea that we are ultimately interested to use graph models to make statements about the indirect influence of things is something that I can now nicely link back to this more fundamental historical philosophy of science perspective by making a few statements on what you could call the philosophy of space and time. So that means how we actually interpret things like space, for instance. And for this, it's actually quite enlightening to consider a very simple example of a two-dimensional Euclidean space. So that means we just have points in a two-dimensional plane. So we have an x-coordinate or an east-west direction, and we have a y-coordinate or a south-north direction. So now what we could consider is we could start, for instance, a heat diffusion process in physics at a certain point in this two-dimensional Euclidean space, and then we can actually trace the evolution of this process in the space over time. So what is a mathematical model for that? Well, this is a continuous space. It's a Euclidean space. And we can model this also in continuous time. So we are modeling a continuous time, continuous space system. So it means we can formulate this as a differential equation. And in this differential equation, if you look into our physics textbooks, then we find that there is this, this differential operator, the Nabla operator, the so-called Laplacian operator, which really consists, if you look into that, of basically two second-order partial derivatives. And we one time derive 2 times by x, and one times we derive 2 times by y. So what you could say is that this operator here decomposes the process in the different dimensions of our Euclidean space, namely in the x and the y direction. So that means in east, west, and south, north direction. So this is an interesting observation that brings us back to the very origin of continuous Euclidean space, to people like Leibniz and Newton, because they had a famous dispute about what continuous space actually is and whether it actually exists as a physical entity. And what is interesting is that Gottfried Wilhelm Leibniz was basically proposing that for him, space didn't really exist, but it's just an abstraction, a mental abstraction that allows us to say something about the set of all possible relations between bodies that can have certain positions in a space. So that means for him, was just a mathematical formalism that may not necessarily exist. And they had a famous letter exchange on exactly this point, Leibniz and Clarke. And Clarke was actually was basically taking the position of Newton in this dispute. So it means what we're actually doing, if you're modeling a dynamical process here in the Euclidean space, is basically we're having a formalism that allows us, and now we're getting closer to the network point, that whatever we actually consider as points in the space, like for instance, the red and the orange point, and if we want to understand how the red point can basically influence the orange point, this formalism allows us to decompose this into the fundamental dimensions of this space, right? That's basically what we see here, the east dimension and the north dimension. And now we could actually transform this problem, this exact problem with a two-dimensional space into a graph representation simply by discretizing our two-dimensional space. So that means instead of now XY coordinates, we can discretize this into nodes, into a lattice network. So it means we can just say we have 9 different nodes that are positioned here, and then those that are lying at the same position in one dimension, they are connected by a link. So this would be a discrete analogon to a two-dimensional Euclidean space. So what happens now is that if you're modeling the same diffusion process on this system, we can actually use the very same differential equation because we still have a continuous time process, but now our continuous space has switched to a discrete space. And now the role of our Laplacian operator, which was a differential operator for a continuous space, becomes a discrete matrix operator, which is the Laplacian matrix. And this Laplacian matrix is nothing more than a specific matrix representation of this graph here. And this matrix representation, or analogously, this graph, is now a discrete representation that encodes this topology of the interactions between the different lattice sites. And you see that the point why we can actually use a matrix for this is it does exactly the same thing, because this matrix or this graph allows us now to decompose the indirect influence between any pair of nodes, like for instance the red and the orange nodes, into the fundamental dimensions of the system. And the fundamental dimensions of the system here are actually the edges. And here we have horizontal edges, that's the east-west direction, and vertical edges, that's the north-south direction, that are represented by different colors. So that means we could say we can actually understand that the red node can influence the yellow node because we can find a move from here to this blue entry, which captures the presence of this link, to the green entry, back to the orange entry. And this is a representation of a path in this network. So now, from this point of view, the power of network science and complex networks and all of the graph learning and graph representation techniques that I have talked about is that they actually allow us to generalize this very idea that we're using to model things in space to arbitrarily complex topologies. Because now, just by changing the link topology to something that does not correspond to a lattice topology that is a discrete expression of a simple Euclidean space, we can model the same process, but you see now all that changes is the matrix entries change. So this encodes now a different topology that is more complex. But you see, an important foundation of network science with this generalization of the topology does not change. We make the assumption that the direct interactions that are captured by links can be assembled into more complex paths that capture how things can indirectly influence each other. And this is a fundamental limitation of using network science techniques, because whenever we use a matrix representation of a system, and then we use, for instance, matrix decomposition, matrix powers, spectral analysis, we always make this fundamental assumption. And what I have just showed you in this little toy example about dynamic networks is that the directionality of the error of time in dynamic networks leads to the fact that this assumption here is violated. So that means we can have a link from A to B, we can have a link from B to C, and still it can be that A cannot influence C via B, simply because the temporal ordering of these interactions is wrong. So you see, this shakes the foundation of network analysis because it kind of invalidates this generalization of Laplacian operators to graph operators. And this makes us wonder how we can actually extend results, like for instance, on epidemic spreading, diffusion processes, clustering, controllability of networks, generally modeling dynamical processes in networks, or also node centralities, actually to time series data, because most of these works here have not considered that the temporal ordering can break this fundamental assumption of network science. And indeed, in our works, we could show that if we account for this property of real systems, we get very different results than what we would predict based on network models. So the bottom line here is network models are very powerful because they can encode arbitrarily complex topologies. But the problem is that real topologies in systems where you also have a temporal evolution of the interaction topology in terms of who can causally influence whom can even be more complex than what a network can possibly capture. And that can lead to wrong statements about complex systems. So that means networks are not basically the final answer to modeling complex systems. But how can we address this problem now? And again, we can take a bit more of a fundamental theoretical perspective on what we're actually doing if we are modeling, for instance, these temporal sequences of interactions with a simple static first order graph model. So what does this mean? What we have seen here is we have two different temporal sequences where in one of the temporal sequences, the path ABC does not exist, like in this one, where here actually it exists. A different way to view this is that whenever we have time-ordered data on interactions, we actually don't have just a collection of random interactions, but we actually have information on a directed acyclic graph that tells us something about the causal structure of the system. And what we are doing, if we are basically just using the edges in this graph, is we are kind of making a maximum entropy assumption about the system. So let me explain why this is the case. The maximum entropy assumption is basically that the only information that we have about the system is we know the statistics of the direct interactions. That means the edges or the links in the graph. And we have no further knowledge about how those links are basically ordered in time and what kind of causal topology this gives rise to. And that means if we have no such information, we have to make simplifying assumptions. And one possible simplifying assumption, which we can actually show corresponds to a maximum entropy assumption on the resulting causal topology, is that basically we have transitive path. That means whenever A is connected to B and B is connected to C, it's actually reasonable to assume that there can be an indirect influence from A via B to C. But if we have information on the real system, this assumption may not be justified. So that means what we could say is that a network model for such data or for such systems is actually justified as long as we know nothing about the temporal ordering. Because then we are not making a mistake. We just use a most simplifying assumption. But if we have additional information on the temporal ordering, then this questions whether we should make this assumption. There's also a different perspective on this, which now leads us very natural to something that we can call a higher order graph model. Well, what are we actually doing here? In the red links, the weighted edges here, we are capturing the statistics of edges in the temporal sequence, or we are looking at the edges in those directed acyclic graphs, right? But an edge is also a path of length 2, a causal path of length 1. So that means an edge is a one-step path. And we know that this one-step path can exist. But from this point of view, you could say this is just a model that gives us path statistics of length 1, when our actual data also contains path statistics of length 2, of length 3, and so on and so forth. So from this point of view, you could say this is a first order representation of the causal topology of both systems. And in this case here, the first order representation of those two systems happens to be exactly identical, because the statistics of the path of length 1 is identical, but not the statistics of longer path. Now, the point is, we can utilize this perspective by making a higher order transformation of the graph, and we can represent our graph in a higher order graph space by making a line graph transformation. So basically, what we are doing is we are replacing the edges in our standard network model by nodes in what we call a second order or higher order graph model. So it means we represent the edge AB by this red node here, and all of the other edges that occur by nodes. What is beautiful now is that this gives us a space where in the edges and in the edge weights, we can now capture the statistics of causal path of length 2. So that means one second order representation of the system would capture that, for instance, the path from A, Y, B to C in that sequence occurred 2 times. And this is represented by an edge with weight 2, connecting the edge AB and the edge BC, which are the second order nodes in this second order edge representation. So from a theoretical point of view, this is a specific type of a k-dimensional de Bruijn graph model for the causal topology of the system, where we actually preserve causal path statistics of length 2 rather than causal path statistics of length 1. And the beauty of this is as well that we can just see standard weighted graph representations of timestamp sequences as a one-dimensional de Bruijn graph model, which now naturally generalizes to higher order dimensions. So what's the point of using this representation here? The point is that for these two sequences here, the first order representation was the same, but you see that the second order representation changes. And this is beautiful because what we can show is that actually the second order representation is the simplest possible higher order representation that is still affected by the temporal ordering in which the edges occur. Because here you see the change of this order has led to the disappearing of this edge, which captures the fact that A cannot indirect influence C via B. And what is also nice is that we again get a weighted graph. And this gives us an opportunity to generalize network analytic methods to those higher order graph models for time series data. And you will probably already notice that there's a very natural way how we can generalize the second order to third order, because we can just put a line graph transformation again here and replace the second order links by third order nodes, and so on and so forth ad infinitum. So what we can also do in terms of modeling dynamical processes, and that brings us back to our philosophy of space and time, is when we can now basically generalize this Laplacian matrix representation to higher order Laplacian matrix representations that basically capture some aspects of the causal topology, and that, as we could show in those works here, allow us to better predict and control dynamical processes in networks that are also dynamic, and where the temporal ordering actually influences the causal topology of the system. So that means that can help us to better understand, for instance, epidemic spreading, but also to better control processes in systems that are themselves dynamic in terms of the topology. So, and this is the point where I would like to make a little interactive demonstration. And now I have to watch actually the clock. So we did start.
Still have 15 minutes.
Oh, so I'm already over time. Yeah.
No,
so
5 minutes for discussion, and to finish your presentation is all fine.
Sorry, how much time is left? I'm
15.
15. Okay, good. So then I think I will just close with this interactive demonstration. So I took much more time than I had anticipated, because I have brought you a little demo where I actually showed how we can actually represent bibliographic data, which is one example of complex multidimensional, multirelational, and time-resolved data based on different types of higher order models in Python. And I'm going to show a software package that we developed at our chair, which is called PathPy. So let me just start by importing this. And so what I'm using here is I'm using, let me just switch off this mode here so I can show you also the data. I'm using a data set where we have, this is just a small toy example, where we have actually information on certain authors with an ID, a name, and an affiliation, certain papers, and then we have, as usual in relational database design, we have maybe some kind of a table that captures a relation between the authors and the papers. So how we can actually represent this in terms of a graph model is in terms of a bipartite graph, which we can do in PathPy by reading this relation author-paper CSV in a bipartite network. And we consider this an undirected network because the relation exists in both directions. So it means now we have a bipartite graph where we have nodes that represent the different papers, and these are the orange nodes, and the blue nodes represent different authors. So we can also check in PathPy whether this is actually a bipartite network or a multipartite network, which means we can actually split up the nodes in different partitions or different types, like here authors and papers. And bipartiteness means that there's only edges that connect nodes in different partitions and not within it. We can also check the attributes of those nodes in our network representation, and we find that the only information that we have right now, for instance, on the paper NatFis 19, is that it belongs to partition 1, so that means it's a paper node, and the only information that we have on author IS is that it belongs to partition 0, so that it's an author node. What we can do now is we can add this additional information in the other CSV files to the graph by adding the attributes. And what we see then is that we can add this additional meta information, like the title of the paper, the journal, and also a timestamp, like that this was published 2019. And we can do the same with authors, like a name and an affiliation. So now, what are we doing, for instance, if we are constructing co-authorship networks from such a simple bibliographic database? Well, we are actually usually making a so-called one-mode projection. So that means we are projecting the bipartite network on one of the partitions, and we are obtaining a dyadic graph representation that, as I said before, loses information on the different co-authorship patterns in terms of larger groups of authors. So in order to create such a one-mode projection in PathPy, you can actually take the bipartite network and project onto partition 0, that would be the authors here, and then you get the co-authorship network that results from this data set. So what we can now also do is we could project to the other partition, obviously, that would be another one-mode projection. And we can also check in the projection on the co-authorship relations. For instance, we can check the co-authorship between me and Frank. And we see that this is actually a multi-edge graph because we have 1, 2, 3, 4, 5 joint papers here in the data set that relate to different papers. And we can also look at the attributes of those papers. And then we see that we have retained information on the title, the journal, and the timestamp. Good. Now what we could do with such a representation is we can create an adjacency matrix, and we can use that adjacency matrix, for instance, to model random walks. And we can, for instance, run such a random walk, and with PathPy, it's also easy to simulate this. So let's start at me in this random walk in this co-authorship network, and then we can actually just press play, and we see how the walk actually walks through this network. This could now be the basis to apply measures like PageRank or to use spectral partitioning to detect clusters. So now we could use different types of higher order models to retain more information from the original data, because we have seen that we lose a lot of information by this projection, because we lose information on who co-authored with whom on which paper, who worked on papers in the same journal, and so on. For instance, we could use the edge attribute of the journals to split up the network into multiple layers that refer to authorships on papers that are published in a certain venue. Like, for instance, these would be the authorships in Nature Physics. These would be the authorships in the PNAS. These would be the authorships between authors in ICSI. And importantly, in such a layer, still, this can be an aggregation of multiple papers that are published in the same venue. So it means we still lose some information, but we retain some other information. So what we could also do is we could split this up in a way that, so here what we have done is we have also retained the nodes, so that would be a multiplex network. We could also do a multi-layer network where we don't have to retain the nodes, and we get layers where the nodes can be different in each layer. So that would be the basis to do this modeling in terms of multi-layer structures. So how can we now retain the information on non-dyadic relationships in terms of co-authors? Well, we can use a projection again in terms of polyadic interactions, which is again supported by PathPy. So you can actually do a one-mode projection, but you specify that you do not want to use dyadic interactions. And what this does, you see, it automatically returns a hypergraph with hyperedges. So now you see that we have an edge between Frank, me, and a co-author that relates to a paper that we have published together. And we can also plot those hypergraphs using this type of visualization where we have these more complex links, like for instance here, that indicate that a group of 4 people, like Frank, Dirk, and 2 others, have published one paper together. So this would be a basis to use polyadic interaction models. And what we can now also do is we can actually apply this idea to create higher order models for the causal topology that is due to the temporal ordering in which the co-authorships occur. And for this, we can again do a one-mode projection in PathPy, but instead of preserving polyadic information, we actually preserve temporal information. So we say we want to have the temporal information in the returned network. And you see that what we get is actually a temporal network. And also the visualization automatically includes a time axis. So I can press play here, and I see how those co-authorship actually evolved between 2011 and what was it, 2023 in this case. So if we compare this to the static network, you see that there's a lot more information in this temporal ordering that actually now translates to this directed acyclic graph structure that is actually the causal topology of the system. And again, PathPy includes methods how we can actually preserve that information. We can turn such a temporal network into a directed acyclic graph. And what we get is a very complicated representation, which tells us basically who at which time can influence whom at which other point in time. So you see this second indexing here is the state of an author in a given year of the observation. And what is interesting here, let's pick a specific example. From this network representation, you would, for instance, you could infer that I could indirectly influence Dirk via Frank based on our co-authorships, because I have co-authored with Frank and Frank has co-authored with Dirk, right? So maybe some ideas can spread in some way. But if you look at the real sequence, you see that this is actually not possible, because Frank has co-authored a paper with Dirk before I co-authored a paper with Frank. So that means there is no way how I could have influenced Dirk, but it could have been the other way around, right? And that is an information that is lost here in this graph representation. If we now look at the causal topology here, we would actually, if we look closely, we would be able to see that, because for instance, if you look here, we see probably that here a path starts at Dirk and ends at me via Frank, but not the other way around. If we look at all of the paths that start at me, you would see that that Dirk can never be a target in this. So you see that here the causal topology consists of different components that are due to the timing, and we have a single connected component in the static graph. So with PathPy, we can also calculate all of the possible path statistics in such a temporal network. And that is basically a collection of paths that we get. So for instance, here would be a path that indicates that, I don't know, for instance, there is a path. Well, actually, here's the path that we're talking about. The path from Dirk via Frank to me. But you would see that the opposite path is not in here. What we can do now is we can use higher order networks, just as we use standard network models, to basically fit them to this path data set and to represent the causal topology of the system. And here would be a first order representation in terms of directed links. And now I can also generate a higher order representation, like here a second order network, where we have the nodes being the links and the links connecting the links via path. And again, we would be able to see that in this network, we see that there is no path, for instance, from Dirk via Frank to me, but again, in the other direction. We can also compare this to a null model, which is what we would expect just based on a network topology if it wasn't for the temporal ordering. And you see again, in this system, there's a single connected component. And we can now very easily extend dynamical process models on those higher order graph models, for instance, by just simulating a higher order random walk on the second order graph and visualizing it in the original network. So if you play this random walk now, you will see sequences of nodes that are influenced by the temporal ordering in which the edges occurred. So that means you will never see a sequence of nodes starting in a forbidden sequence based on the time series. And then obviously we can also generalize this to third order networks. So it means now we can have this generalization where the nodes are path of length 2 and the links capture causal path of length 3, and we can use that to model the system as well. Okay, so that gives you just an idea how we can actually use different types of higher order models to advance network science, be it multi-layer networks, hypergraphs, simplicial complexes, or these higher order path models that capture the causal topology of systems. And I would like to refer you as a little reference to some interesting exemplary findings that have been done, that have been made in the community over the past years about community detection, the use of high order models for ranking, for studying dynamical processes, be it multi-layer networks, be it hypergraphs, or be it the higher order models for causal topologies that I introduced. So to close, I would like to ask the question whether this is now giving us a new age for network science where we can actually extend everything that we learned to these more interesting sets of models. And so basically after theoretical foundations, interdisciplinary network science and machine learning, is it now all about higher order graph models, and we are also all happy with this ending? And I would argue that this is not the case, but I would rather say that these different models introduce basically fundamental challenges for all of the different ages or all of the different lines of research in network science, be it theoretical foundations, interdisciplinary network science, or machine learning for networks. And I will close just by giving you a very brief overview. I have a little demo on this generalizability prepared as well, but I will just skip over this, but I'm happy to share this as well. The first challenge that I see is practicality. So one of the benefits of standard graph or network models is that they are easy to understand, to construct, to analyze, and also to visualize. The problem with higher order models is that we are operating in higher dimensional spaces that can be very, very large. So that means we can have even small systems that have tens of thousands, millions of nodes. And that is something where we have to develop new techniques that basically facilitate scalability, for instance, by using the sparse structure of many higher order systems, or that also address questions of data efficiency. So we have done some work recently where we can show that using Bayesian techniques to infer higher order models allows you to use orders of magnitude fewer data on interactions to accurately model a system compared to standard maximum likelihood techniques, for instance. We also need new techniques to visualize such systems, because visualizing systems in a higher order space is not very useful, because we are used to visualizations where actually the nodes represent entities in the real world. So that means we need techniques where we actually use higher order structures to visualize a system in a first order space. And that is something that we have done, for instance, where we can generate first order cluster structures that have been detected using higher order models. So there's a recent paper on this. A second challenge is about generalizability. And I think this is an important challenge for machine learning. And I would just like to skip over this, and I would just like to leave you with those questions. As soon as we have degrees of freedom on how we want to model a system, that raises the question, what model is best? So that means we can now go to different orders, or we can even go to different paradigms of higher order models. So that means we now have decisions to make that we couldn't make, that we didn't have to make before. And we also have to answer the question when we actually need those higher order models, and when standard first order models just with nodes and links may also be sufficient to model a system. So very quickly, this is fundamentally a machine learning problem that we have to address. So that means we have to use machine learning techniques to derive optimal models. We can also validate those models, and we can actually show that those models give the best predictions. We have done this, for instance, for our models for time series data. And the third challenge is a fundamental theoretical challenge for the next years, which is, you could call it reunification. So these different paradigms are basically currently incompatible with each other, but they are all based on the universal theme that the topology of complex systems cannot be decomposed simply into dyadic interactions. And they also see standard graphs as a lossy representation for complex systems. But they all use different but similar mathematical abstractions in terms of, for instance, tensors, generalized adjacency matrices, higher order Laplacians. But we cannot currently move between multi-layer, higher order de Broglie graphs, simplicial complexes, and hypergraphs. They all have their different assumptions. So an important question would be whether we can develop what you could call a unified theory of higher order graph models, which is also very important for the network science community, because we currently see a split between different camps that are working on very specific problems, sometimes very isolated from each other. And also we need those models because currently we cannot really combine them, for instance, to model, I don't know, causal path in time-stamped polyadic interactions, or typed polyadic interactions, or networks with polyadic motifs. These are all challenges that have not been addressed yet. So the conclusion of my lecture would be that there is no single model to rule them all, and networks, simple networks, are certainly not that. But we need to understand the strengths, weaknesses, and assumptions of different modeling approaches and model families. And there's a couple of key challenges here that I have highlighted, and that we also have highlighted in this perspective article. And I think this gives rise of an exciting research area at the intersection of complexity science, data science, and machine learning that I hope many of you will address in the next decades to come. Thank you very much for your attention.